Okay, so hi everyone. Today I will present you our research here. The name of this work here is FastMig, leveraging FastFreeze to establish robust service liquidity in Cloud 2.0. So let's begin with what is Cloud 2.0. Cloud 2.0 marks the next generation in cloud computing, integrating cutting-edge technology like AI, machine learning, and IoT. This phrase emphasizes greater efficiency, scalability, and use of heterogeneous resources, setting the stage for advanced and innovative applications. Services have to be truly distributed, either across edge to cloud or across multi-cloud. That is, the service must be free to execute and relocate seamlessly. We call that service liquidity. Service liquidity also provides key benefits for daily IT operations. It simplifies maintenance, tasks, and optimizes resource utilization by dynamically allocating workloads across systems or clouds. And of course, a robust live migration solution is hard to achieve service liquidity. So let's talk about some background here. As you may know, container is become like a standard way to serve any services. It provides service isolation, packaging up dependencies, and also portable. Container migration can be benefit for service provisioning through load balancing, fault tolerance, and of course, the service liquidity. On the high level, for live migrations, the containerized service migration can be done by checkpointing the service inside the container, moving the checkpoint files to the destination and restore the container to its original state. Mainly, you want to checkpoint the process states, the memory footprint of it, and maybe some files or persistence data or logs. So, CREU. The full name of CREU is Checkpoint Restore in User Space. Has been the main tool for checkpoint and restore application, process state, and memory footprint. It can be used with other techniques as you may heard to mitigate migration delay like pre or post copy. Another interesting tool that we use here in our project as a foundation is FastFreeze. It's built to especially for container checkpoint restore. It is lightweight and fast. It also takes care of container file systems. It essentially uses CREU as its main engine for checkpoint and restore. But FastFreeze comes with some problem if you want to use it with live migrations. It did not design for migration, as I said. Its command line only make it hard to integrate with existing system and integrate with any other system for migrations. And one of the major problems is that when using with multi-process application, which is widely used, for example like database or something like, or maybe machine learning application, it produces significant restoration delay, which highly affect live migration formats. But before the potential of using FastFreeze to be the foundation of robust live migration solution, so we adapt this to be FastMig. We mainly separate the layer. So for the overview, we mainly separate the layer of the container into 3 layers. The container management layer, which is the existing container runtime. The service execution layer, which is where the service actually running and the checkpoint restore happen there. And the main part that we develop here is the service management layer. It's where user can manage how to checkpoint restore, maybe and fault tolerance, and providing easy to use interface. So let's take a look into it. So by doing that, we separate the service lifetime and container lifetime. What does that mean? It means that even the application stop, the container don't have to be stopped. And that open up opportunity to manage service even better and easier. We use this to state 3 startup options, namely from scratch. It's like you start the operation newly from the beginning or from any checkpoint that you would want. Or the last one is in the standby mode. Is that only plain container but no service is startup yet. This can be great benefit for live migration. For example, we can do operation called warm restoration, which let the container start at the destination before the state migrate to it. Speed up the migration time. We will look at the improvement of this operation in the evaluation part. Another one is we provide the fault tolerance mechanism in the management layer. It is a self-feedback method. Mainly, it is a log analysis from the application and determine how the container restart when the failure happened. We use a startup option as we mentioned before as the choice how the container should be restarted. So user can define their own logic of this log operations, this log analysis logic, how the container should restart when they read the log. For example, there is some simple logic here, which is just read the exit code of the application from the log and then determine how should the container restart or the service restart. Another thing that we another work here is that we improve the multi-process restoration time and affect the migration time, obviously. So we investigate the root cause first. The root cause of this is because crew want to restore the process with the same process ID as when it is checkpointed. So it have to control the process ID when the service is restored, and sometimes there is not enough permission. It have to use another way around, like FastFreeze use fork bomb, which is just continuously spawn new process and kill it till you get the desired process ID. For one process, it is not that affected, but for multi-process, the process has to go all the way to the maximum process ID possible and come back again to get a design and do this again and again. As you can see, it can produce dramatically long delay. So the solution here is that we have to provide enough permissions and enough capabilities. So introducing in new Linux 5.6 kernel, there is a capability called cap checkpoint restore, which allow modification of this file ns/pid that control what the next process ID will respond. But that's not enough. You have to allow writing to some protected area, especially when you run with container that will be protected area. It is cover this file as well, so you have to allow that with this security options you see, but that can be dangerous. Maybe we add some custom app armor profile to protect that file system while still allowing writing to this file, and that's open up the ability to control the process ID and fasten up the migration tab. So for the evaluation, first for the setup, we use two Ubuntu 22.04 virtual machine, each with 4 virtual CPU, 16 gigabit memory, and 100 gigabit disk storage in FastMig 7, and both reside in the same network, so we can neglect the network performance when we do the migration time measurement. We use Docker as the main container engine, version 25, and we use two main applications for following experiment. We use memhock, a widely used memory benchmark which randomly allocate memory time and time in a static range. So this application represents a static memory usage application or service, and another one is YOLO v3 tiny to represent some more realistic application and a dynamic memory usage. It is a object detection application. We mainly use it in the inference part when we benchmark it. So first, we have to look into the overhead of the FastFreeze and the FastMig when there is no migration yet or in normal operations. So there is no migration. The application is the memhock is just running by itself. It's just allocating memory time and time. And as you can see, there is very small increase in CPU usage and memory as there is more process. As you can see from the overview, FastFreeze have to spawn another parent process to take care of their child, and also FastMig have some component that need to control, like interface, like FastFreeze daemon. So, but we can say that the overhead is very small and can be negligible. And for the performance overheads in the normal operation also, you can see that there is no difference at all in the performance, in CPU speed, in memory bandwidth, network bandwidth, write IO bandwidth, or read IO bandwidth. So there is not the user should not concern about the performance or overhead when using in normal operations. Yeah, we talk about we improve the multiprocess result migration time. So we compare between the FastFreeze with proper config or with our fix and without our fix. As you can see here, the improvement is very big. For 2 process, it is 30-second improvement, and for 16 process, it is 450-second improvement. It's about 80 time improvement. So as you can see here from the graph, improvement it mainly come from the improve of restoration time, because we can control how the process ID will be in the future. And yeah, we have to, and we measure the live migration overhead here. You can see that with warm, and we also doing warm restoration here. So you can see that the checkpoint time is similar, not that different, but the restoration time, as you can see here, is smaller, but it's hidden that is because it's hidden the time, because restoration time including the time that container startup. So when we can hide that startup time, that effect with port exposure, you can see that it improvement is a lot. Maybe port exposure may be some kind of unrealistic, but many things can affect the container startup time, like image layer size, or the memory usage, or the file system, or mount file system of the container. If you use this warm operation, we can hide all this startup time in the migration time and improve our live migration performance. Another thing that we experiment is the impact of the fault tolerance mechanism. So we decide to benchmark it with different function with different string process logic as the function to analyze the log and produce the answer with the 2000 line appreciable block. So we can see that when we use the fault tolerance logic, there is some overhead, but it's relatively small with around 0.2 second, and it is linear regardless of disregarding the time complexity of the log analysis function. Additionally, lastly, we experiment the coverage of the fault tolerance mechanism when there is certain fault scenario will happen in each phase of the migration time, namely normal operation, application, checkpointing, and restoration. So most of the case is valid, as the valid is mean that the application can be continued when the fault is fixed. But there is some point that is problem. For the network failure during application restoration is an exception. This happens because the FastFreeze will wait. FastFreeze at the destination will wait for the checkpoint files from the network file system, but the network is failure, so it cannot be reached, and it will wait indefinitely for the reconnection, so it is not restart appropriately. Additional, maybe user need to fix that also by hand. There is also another two limitation of the fault tolerance. So if the fault occurs during service checkpointing or restoration, the progress of the interrupted process is discarded. So if you checkpoint and there is failure happen, if it never happen, then the next attempt to the operation for example, a second restoration for the same checkpoint file is started from the beginning as it has never happened before. So secondly, for system and hardware failure, the behavior may depend on how system or operating system acts on the container. For instance, maybe if the operating system shut down gracefully and sent termination signals to the container process, the fault handling module will control to restart in the standby mode. But if not, if it just shut down, the logic doesn't have any chance to evaluate the fault. So it will begin as a default mode, or will be the state that indicate in the starter option from the previous function trigger. Yeah, so that's all. And this is our conclusion. So we can say that FastMig leverage FastFreeze to establish a robust service liquidity as a robust live progression solution. It's do that by decouple service management layer for execution, allowing pre-restoration, improving live migration time, fault tolerance mechanism to make it more robust, providing standard interface for easy system integration, improving multi-process live migration by reduce restoration time and reduce overall live migration time. That's all for me. Thank you.